This is Process Control Signals, Part 2. In our last video, we talked about some neat electromechanical devices that we developed over the years to do all the hard work. And we did a lot of talking about some of the terms, etc. And at the very end, we've kind of looked at a quick thumbnail sketch of the formula you use to calculate um, if your signal is on track. We're going to look at those formulas now in a greater detail. Also recall that we discussed range, how it was associated with the process variable, and span was associated with our signal, and that in a perfectly designed system that's all calibrated and working, that our change in our process variable should be mirrored in our change in our span or our signal out so that they're in sync. Now, when we're doing that, once we know we have that done, we can then use that information and we can verify without getting any of our, as long as we have a way of visually seeing the process variable and have a way of testing the current voltage, we can see if it's calibrated properly or if it's needs to be adjusted. And we can also predict what the signal should be, or we should have a signal, we should be able to predict what the process variable would be. So we're going to look at those formulas and go through them in a little bit more detail. And you'll find it's basically what we did, but focusing that we get all of the information. Recall that both sides work together to make the process control system work. And the following one, we're going to start with the process variable, and we're going to convert that into a usable signal. So the complete get everything involved formula, the process variable is equal to our signal less any offset that happens to be there divided by our span. Once we have that, we're going to multiply that by the range of our process variable. And the last thing we do is if there's any lower range value, for example, our tank, we had a 2-foot bottom we had to take into account. We put that back, and that gives us our total process variable because we have to keep that 2 feet. If we had that tank again, we still would have to have that 2 feet because that is inside the tank. So let's take a look at this formula in action. So let's say you go to work in a stamping plant that has a large air compressor. So the process variable of our system needs a steady supply of 15 pounds per square inch. As different subassemblies perform their functions, however, the air pressure starts to drop. When the system air drops to 10 psi, pounds per square inch, the compressor pump must fire up. The pressure transmitter puts out a 0 to 5 volt signal. Now that's all well and good, but we have to kind of sort out our process variable components and our signal components and then plug them into our formula. All right, let's start sorting out some of these numbers so we can put them and plug them into our formula. So the process variable is the system air pressure that's generated by the compressor, and it's measured in pounds per square inch of pressure. In this scenario, our range is our upper range value subtracting our lower range value. So we'd like to have 16 psi all the time, but that will drop down as system requirements have it. That's normal. But when it gets down to 10, it has to start up. So this means 16 take away 10 gives us a range of only 6 psi. So the lowest possible pressure in the system is actually 0, but under normal operating, it wants to restart if it reaches down to 10. 0 would be the system completely turned off, locked out, and all the air dissipated. Now let's take a look at our signals. In this scenario, our span is signal max minus signal minimum. But because we're using a 0 to 5 volt system, that's 5 volts take away no volts, gives us a span of 5. This system has no offset. So its minimum signal is 0. So 5 volts of span will represent 6 pounds of pressure of range. Now here, it's pretty clear that the result we get should be close to a 1 volt to 1 pound per square inch. But we have to keep in mind the lower range value. So let's look at a couple of examples, something that might come up in the system. So one day you're walking by and you see that your transmitter is sending out 5 volts. What's the total process variable then? What's the actual amount of pounds per square inch being generated? Now, this should be pretty easy, and this is a check because we've already got that established. But let's go through the math to prove it out. So our process variable, and I've changed the formula somewhat so I can keep in mind that I take all of the steps in the proper order. And the first thing I have to do is I have to take my signal and subtract our offset. Well, that's pretty easy. It's 5 take away 0, which gives me 5. The next thing I have to do is I have to divide that by the span, in which case this is 5. That brings me down to 1. When I'm finished all that, I'm going to multiply it by our range, which in this case is 6 psi. And the last thing I'm going to do is I'm going to add back the lower range value. So this gives us 1 times 6 from our adjustment of our signal and span, plus 10 for 16. Perfect. It's exactly what we want. That's what we were planning on. That's what everything's laid out for. Next day I walk by, and it only says 1 volt. Okay, let's see if it's doing its job. So at 1 volt, we subtract 0 because we have no offset. We then divide that by our span of 5. We take that 1/5 and we're going to multiply that by 6. So that's 0.2 times 6. We still have to remember that 10, that lower range value of 10. So we take our new total, which is 1.2, plus 10 gives us 11.2 pounds per square inch. It should be right on. All right, that formula works great when we know what the signal is and we calculate the process variable. Now, that's assuming, of course, that everything's been calibrated. Having said that, what if you're walking by and you see the pressure gauge, and the pressure gauge announces to you a particular pressure? And you can walk to the transmitter and it will give you a readout on the actual signal that it's got. So the question then becomes, can I somehow rework that formula so that I can verify the signal versus what the gauge is telling me? Okay, we can. All we do is rearrange the formula. So if we want to calculate a signal based on a pressure or a signal based on a process variable value, we simply do this. First, we take the process variable and we subtract from it any lower range value because we're dealing with the change that we're measuring. And the lower range value is fixed and we're not going to do that. So we're going to take the process variable, we're going to take the lower range value out. Then we're going to divide that by the range. Once we have that, we'll multiply it by the span of our signal. And then, just like we had to do before, we had to add back the leftovers, the lower range value. If there's any offset, we have to add that. Using the same system, if the current pressure that you saw on the gauge was 12.7 psi, what signal should be seen at the transmitter? Okay, so our signal is going to be equal to, the first thing we're going to do, and I've broken this apart, so I always keep my order of operation correct. First thing I've got to do, and I've got to remember, I've got to take my 12.7 process variable by the gauge, and I'm going to subtract from that my lower range value, because we only want to get the part that we're actually adjusting the signal for. Okay, so that's 12.7 minus 10, which gives us 2.7. And from that, I have to divide it by 6 because that is my range. I only have 6 psi that we're working with. Once I do that, I've got that number of 0.045. I'm going to multiply that by our span, spread it out. So that's times 5, which gives us 2.5 to 2.25 volts, but I've got to add the lower rate, the offset, pardon me. And guess what? There is no offset. So I should get 2.25 volts signal for 12.7 psi. So working with these two sides of our total instrumentation control loop, you can create a repeatable, predictable, controllable process. In our next video, we will be examining some of the devices that makes all of this possible. Until then, thanks for watching.